We have seen that gradient descent can help us to find the best fitting parameters theta. However, from the contour plot, we can see that depending on where we start from, we can converge faster or slower to the minimum. So concretely, our initial theta values will dictate where we start from and thus how long convergence can take. So with what values should we initialize theta? Should we just set them all to 0 at the beginning, or is there a better value to initialize them with? That's what we'll find out right now. Initializing parameters in machine learning is an important step that can impact the performance of your algorithm. While initializing parameters with 0 is a common practice in some algorithms, it's generally not recommended for linear regression. When you initialize all parameters, theta, with zeros in linear regression, the update steps during gradient descent will be the same for all features, and they will all converge to the same value. This can lead to slower convergence and suboptimal results. So how do we initialize them? In linear regression, where you have a simple linear relationship between input features and output, initializing parameters is relatively straightforward. Since the objective in linear regression is to find the weights that minimize the mean squared error or a similar loss function, you can often use simple strategies for parameter initialization. A common practice is to initialize the parameters randomly. This helps break the symmetry and ensures that each parameter starts with a different value, allowing the algorithm to learn more effectively. You can initialize the parameters with small random values or draw them from a normal distribution. Here's a simple example using Python and NumPy to initialize weights for linear regression. In this example, NP random RANDN generates random values from a standard normal distribution. You can experiment with different initialization methods, but random initialization is a good starting point for linear regression. By multiplying the random values by 0.01, you ensure that the initial parameter values are on a smaller scale, which can lead to more stable training. This is particularly important when using activation functions like sigmoid or tanh in neural networks, where keeping the values in a specific range can help prevent issues like vanishing, exploding gradients. In linear regression, it might not be as critical, but it's still a good practice for consistency and to prevent potential numerical instability. Let's assume we have now 3 features with each feature 5 training examples. This means that we need to initialize 4 theta values, namely theta 0, also called the bias, which corresponds to this feature x0 that is always 1, remember, and the other 3 theta values. So if we now run the code, we see that we get 4 small randomly distributed values for theta. It's worth mentioning that for simple linear regression, the initialization strategy may not have a significant impact because the optimization problem is convex, and you can often find a global minimum regardless of the initial parameter values. However, for more complex models, especially neural networks with multiple layers, the optimization landscape becomes more non-convex. In these scenarios, the choice of initialization can significantly affect the convergence and training efficiency. In those cases, initialization methods like Xavier, Glorot, or initialization, which are designed to address challenges in deep neural networks, might be more suitable. These are techniques we will see later after we have seen neural networks. So for now, we will end this video. If you remain with any questions, please leave them in the comments section below.